So Luke Spaghetti, Spaghetti, Bigetti, I don't know. Luke posts this question on Twitter saying, hey, any vector folks out there, I'm looking to find out where this point and this point cross through this box and what that point of intersection is. And so I replied to this saying, no problem. Y equals mx plus b. Yeah, people didn't like that answer and said that I was just telling them to draw the rest of the owl. So let's take a moment here and as programmers break apart the problem, solve it, and then see if that comes back to a solution somewhere in math. Let's get started. Okay, let's start off by taking a look at the problem. Would you agree that if we could find any single point that we wanted to along this line, that we could easily find the one point that we're trying to find here? So if we could find any of these points, then we could find this one. To start this adventure, let's take a look at how we define a line. We define the points at the beginning and the end of the line by how far they are from some particular y and some particular x. For right now, let's pretend that that x is equal to 1. That would mean when y is at its highest point, let's say it's like 5 or whatever, that would actually be equal to y times 1, which would be like 5 times 1. And as that scales down into 0, that would be 5 times 0, which would bring it all the way down to 0. And this scale interpolates perfectly between 0 and 1 if x is equal to 1. So we could actually make an easy formula to find wherever you are on y by saying just multiply y, which is 5, times whatever we are on x, and that interpolation will happen just fine. Now this is fantastic, except for sometimes x is just not equal to 1. But as your developer brain might have just told you, we can solve this with proportions and scale. See, we're always scaling things to be values between 0 and 100, or 0 and 1. And this goes back to your basic math that you were doing in school, where if you scored a 4 out of 5, you get 80%, or 16 out of 20, or 18 out of 100. What we simply are doing is we're normalizing this to some degree between 0 and 1, or 1 and 100. So if we move over to the left, -5, and up, -10, well, then you might be wondering why we're moving up -10. And now the answer to that is that we're using a screen coordinate system where as you go away from the y, you start to increase in value. So going up is actually going negative. We see this often in software design because the origin point is considered on screens at the top left, 0, 0. So then when you are going down, you're going into the positive y. If you're thinking mathematically, this is usually not the case. Usually you go up for positive, down for negative for y, but computers. So let's just go ahead every time we're going up, because that point is going up and to the left, it'll be -5 for the left, but -10 because it's going up from an origin point there. So a moment ago, our proportion was 1x to some amount y, but since it's not going to be 1 now, we need to figure this out. In order to do that, we'll find the proportional growth by dividing it, the amount y by the amount x, and that'll give us the value 2. So now we know that this line will grow specifically in the y value, depending on whatever x value we give it. So if we give it x -5, it grows to -5 times 2. And this formula continues to work for every single point in the line. Go by -3, that point will be -3 times 2. And then, of course, if we go by -2.5, it's -2.5 times 2. So this ratio that we found out, this proportion of dividing them, we can find this x. And so we go to look at this x value, but uh-oh, there's a problem here. You see, all we have is its y value, and now we have to go backwards. We have the y value, but we have to figure out what the x value there is. The y value is right there in the box coordinates because that's a straight line. But we don't know what x this is. So this messes us up for a second. But we got this. And to do this, we're going to call on our old friend, Mr. Algebra. We have a formula for y, and so we can easily use algebra to go ahead and divide both sides by 2 and find a formula for x. And x is going to equal to y divided by 2. And that makes sense because we were multiplying by 2 to go one direction, we divide by 2 to go the other way. And so with our proportions in hand and our formula in hand, we could figure out that y here at -5, we use our formula, which is divided by 2, and we can solve for this particular line with x equals y divided by 2. That'll give us -2.5 and -5 for this point of intersection. Now, that sounds fantastic because we went through a lot of work for this line, but let's go ahead and take a step back and think about how this should work for any line that has an origin at 0, 0 going to some particular point. We could find the proportions for those lines just as easily, and using that, we could actually figure out the point of intersection for multiple lines, including this one and even this one. So let's take a step back and put this into code and generalize what we just learned. So if we're looking at the code here, I did the box top y, which is -5, and that's the top line that we're intersecting with. The outer x, which is the line outside of the box, which is outside the origin, and the outer y, which is -10, which is outside the origin and outside the box. And so we can figure out from here, we need to go ahead and figure out those proportions. Now, one thing I want to do here is rather than doing all that algebra, I'm just going to flip the x and the y, so that way we get the inverted formula here for the proportion x on top, y on bottom. And that way it cancels out specifically, so that way we can figure out the y value that we need. And so what I'm going to do here is get the result by proportions times the box top y. That's the number that tells us where we're at. And if you want it in a cute little finder formula right there, you can see it all in one particular line. If you had to have a generic formula for anything that's inside, starting at 0, 0, going outside the box, and then immediately detecting where it hits the top of the box. Now, if you noticed, I was being terribly specific talking about this line. It has an origin inside the box and crosses through the top of the box, and that would work for this line or this line. But what if you have a line that doesn't work specifically this way? Perhaps there's one that doesn't come from the origin. So you might say, let's see what happens when we try to do this. Well, the first problem that you might notice is that when you detect that top point right up there, you'll notice that that point is actually going to say it's at -1 here, when actually the distance it's actually traveling is -6. So we want this green line and not that yellow line. Because it's not from the origin, we need to go ahead and figure out what this number is by subtracting the x values to get that actual distance along x and that actual distance along y. And then when you get those actual distances and divide them, that will give you the proportions ratio that we've been looking for. That way we're just able to get these points independent of the origin. So if we were to take a look at this with code, I have the box top y still there, and then I'm destructuring the x1 and x2 to keep them grouped together. But you can get the x length and the y length, and then you can calculate the proportions with that using x1 and x2 for any 2 points on the line there, and that will give you the proportions that you can multiply by the x top y. And if you need that all in one nice little finder formula, there it is again. But don't go ahead and start copy and pasting this code just yet. There's a chance that there's still an issue. So let's go ahead and run this through with some actually formulaic solution to the line and see what happens. So we had our x2 minus x1. We'll plug in the numbers there, -4, -2, and we'll plug in y2 and y1. And when we do this math here, we come out with a ratio of 1/2. Uh-oh. That's not good because that's exactly the same value we came up with just a moment ago. Remember this blue line that we had? When we put this blue line in place, we found that it actually landed at 1/2, but then we added this pink line, and there's no way that that crosses through exactly half of whatever the x value is. So we can calculate the x there. That's what we used there. So what's going on here? Well, if you take a look at the line, it's actually completely proportional and it's a parallel line to what's going on here. And when we measured and we subtracted these points out, what we did is we kind of removed where it was. We brought it to the origin so we could get that ratio. That means that we need to shift this line back over because we want the ratio, but we also want to know how far it's shifted over inside the x-axis. And so now, because we don't have a point in the origin, we got rid of it, and now we need to add that shift back. So assuming that we have to now shift x by some value, let's figure out what that value is using our old friend algebra. We'll simply add that value in. X equals y times 0.5 plus some number, we don't know what it is yet. And then we'll go ahead and take some points that are on that new line, x1 and y1, and we'll put those in for x and y, and then we'll solve for that question mark there. And 2 equals 1 plus some number, and that means our x shift is by 1. So if we shift all of our numbers by 1 once we do our solution, we have our new line that's not actually at the origin. So let's bring this back to JavaScript for a moment. We have the same code we had before, the box top y, x1, y1, x2, y2. We found the length with x length equals the subtraction, the difference between the x, and the y equals the length, the subtraction between those, and the proportions were found, and that is correct. But we do need to find out how much we're going to shift x by. And so we can do this with a simple, you could do it with any set of points, but we just put them back into our formula, y1 times -1 to make it negative, times the proportions plus x. And that's what we just found out just a second ago with our algebra. Essentially what we're doing here is we're finding where the x-intercept would be for this particular line. And like we saw a little while ago, it's shifted over to the side just a little bit, plus 1. We found that value out. So if you take a look at the result here, we have the proportions, which is that ratio, times box top y, which is our point on y we want to find, and then we have to do that little bit of shift in x where we shift it over to the right 1, and that's x shift. So now we have a generic formula, and we have a nice little finder formula for you there at the bottom if you want everything all together, and this handles things that are not in the origin, looking for that point of contact.
Awesome! I came to play, there's a price to pay. Time for you to get down on your knees. I came to play.
So you might be wondering why I said y equals mx plus b when I knew all of this cool stuff as well. Well, that answer is quite simple. If you take a look at what we just came up with and what we solved, you might start to see some of the answers that mathematicians have been telling us for a long time. You see, we were trying to solve some formula that could tell us any point we wanted to along that line. And ultimately, after all our work, we got x is in proportion to the y value plus some kind of shift in x. So x equals our proportions, which is x over y, times the y value we want plus some shift. If you remember, originally, I kind of solved it for y first. Y equals some proportion times x, and then there was a y shift. It was just 0 because we're at the origin. So y equals some proportion times x plus some y shift. These are the solutions that we came up independently by actually sitting there and analyzing and writing code. However, this is actually just y equals mx plus b. Y being the coordinate that we want, m is the proportion, oftentimes called the slope of the line, where we go ahead and we have rise over run, and then we multiply that by some x value, and plus b, because we're looking for y, is the y-intercept. So y equals mx plus b is what we actually came up with. Remember, m is the slope, which is what we have for rise over run, and b is the y shift, and that's just the y-intercept. That's how much we want to shift y for any particular line once we know what direction it's actually going in. This is exactly what we already have here. So let's go ahead and see if the math checks out. Let's go use an online math program to see if the formulas that we've derived actually do work. Now, almost all the time, everybody's referencing y, but there is, of course, referencing it by x. The graphing calculators can do that too. And then, of course, there's a generic form of a line which doesn't really care if it's going to be solved for x or y. So here we are on a website called desmos.com, and it's a graphing calculator website that we can use to take a look at these lines specifically. So if we take a look here, we can see the two formulas up there on the left side one with a purple line and one with a green line. And you can see here we have a negative y here. The reason that I had to put a negative y in our first formula is because a normal Cartesian coordinate system does not normally go the direction like we were using earlier, because y is usually positive going up. So if I remove this y negative here, what will happen is the line will invert along the y-axis and then it'll go the other direction. And so, yeah, this isn't exactly how we had it, because we were using the screen coordinate system where once we go above 0, 0, we're going into a negative domain. So I will put negatives in front of the y's here, but that's just simply so we can compare apples to apples when we're looking at those patterns there. But we can see that we have our purple line, which is y times 0.5, which is halving the line for the x. So every x value at 0, it'll be half of 0, which is 0. So let's explore this purple line. Obviously 0, 0, because x is at 0 and 0 times 0.5 is going to be 0. But remember up here at 10, we wanted to go ahead and have a minus 5 and minus 10. Just remember to add the minus because we have an inverted y-coordinate system on the other thing. But Cartesian coordinates won't invert automatically for you. So if we're taking a look here, you see minus 5, and that would have been minus 10. So we're looking at that. And we can look at any point we want to sort of like check our math here to make sure this line actually goes through the points that we said it would. So we have the origin, and we have the line up there. So if you remember, the box was somewhere around here at minus 5. So if we go to that purple line right here, and if I can land this right about at 5, then we can see the value should be minus 2.5. And that's what we came up with for our formula to find that point of intersection for this particular line. So the formula for the line works here fantastically. And here we have it. So we know that the answer is up here and down there with those 2 points. That point of intersection right there, we can calculate any point along this line and we have our point of intersection. So now let's go ahead and take a look at our line that's shifted off of the x origin, and you can see that it's shifted over by 1. And so we solve this with x equals y, that's a minus y, times 0.5 plus 1. And that makes absolute sense. Don't forget about the minus y there, kind of keeping us a little bit honest. And so that plus 1, you can see we're over here at 1. So the original points that I'd given you were 2, 2. And so if you look right here, there'll be 2 minus 2 because y is inverted. But you can see it 2, 2. So we have that point in place. That looks good to me. And so if we're moving up here from this point, we need to shoot all the way up to 10, where I said the other one was. And that one was at minus 4, 10. Good. So that means that if we actually put this at the 5, we should get that point of... we should be able to find out exactly where that intersection point is. With our formula, we calculated this out. So let's go ahead and go to that 5 there, and we should see, that's right. If we said minus half of 5 is 2.5, plus 1 is minus 1.5. That's correct. That's exactly where we should intersect for this particular line. So now we can find not only the intersection of this line with any other line, we could find any point on the line that we want. And we use this graphing calculator to make sure that all the code and all the functions that we wrote just a second ago actually make sense. And this is one of the great things about math coming in from programming. When you're doing the software and you're programming this and you're guessing where these lines are, or you're visualizing it and you don't have the formulas, one thing that you're trying to do is you're trying to see, am I getting this right? But you can see that with math and kind of coming back from that perspective, we can actually see specifically, yeah, we are exactly correct. We're able to use some free tools on the internet, and then we can see this point of intersection, not only for this one line, but we could double check and unit test ourselves to see that all of our functions would work for multiple lines. So, was the solution y equals mx plus b correct? Yeah. Was it a good answer to something that's just a programmatic appeal to what's going on there? No. And so hopefully in watching this video, you kind of get some of the geometry and some of the basic algebra of what I was trying to get at there. But also more importantly, from a programmatic perspective, we walked through what a lot of classrooms back when we first learned this stuff didn't really explain to us that we derived the formula for a line independent of actually going through and just being told y equals mx plus b. We are looking specifically at how we can derive and figure that out for all lines in all kinds of space. So I think this is a really awesome session. It's a really cool idea to talk about. And if you're interested in learning more about programming and math, be sure to go ahead and follow me on Twitter or just message us at Infinite Red, because this is really cool stuff. And I find that most of my math upbringing was not this much fun, and I'm happy to go over this stuff with you.